I did get emailed a question about some of the homework that we're looking at. Online students, feel free to email me questions. Face-to-face students, we can go over questions in class. So what kinds of questions did you have so far in Chapter 1? Let me see. We'll go to the assignment here. Anybody have questions on Chapter 1? Yes?
The first question.
The first question. I have to make this a little bigger so I can see a little better. One day, Sierpinski began a creation with, as always, a perfect purple square. However, one square seemed too plain, so in the exact center of it, he added a gold square. He saw that the central square implicitly defined 8 purple squares surrounding it. So you see, with the yellow in the middle, now there's 8 purple squares that look like this first square, only smaller. As he pondered, he realized that those 8 purple squares were identical to the original large square except for 2 things. Let's see. Each one of these is smaller, right? So they're about a third as wide and tall. So is that what they mean when they say a third here? Let's check that out and see. They had a gold square in the center. No, these don't have gold squares in their centers. Each one is 1/4 the size of the whole square. No, that's not true. It's not half the size of the whole square. None of them has a gold square in the center. That's true. Let's see if those are the ones. Those are the ones. Okay, so when you try to figure out what they're talking about on that problem, those are the ones that they're trying to get at. Yes?
Can you explain the first one?
Each was 1/3 the size of the whole square. So you're thinking, well, wait, this is a 1/9, right? It's not a third, it's a 1/9. He means lengthwise. So if you took a ruler and laid the ruler down, each one of these is 1/3 the whole length.
Okay, thank you.
Any other questions? Was that your question?
Well, just when we're assigning the quiz, like, I know it's a lot to ask for, like dissect the problem, but like, we're not gonna ask the same question. Like, just the process that showed us this, like, infinity, like, it was like 1/9 times this, and then it just was like how to get that answer.
So you're thinking about, now these quizzes are going to come up, and there's going to be these hard questions, and how am I going to do them, kind of thing? Like, what are you expecting? So I do try and help you know what to expect on each quiz. So during each section that we talk in the video and in class face-to-face, I'll be telling you, this is a good type of quiz problem. So put little stars by those, okay?
Oh, okay.
Yeah, and I'll come right out and say, this is a proof you need to be able to show. This is a type of problem you'll need to know, okay? Because I don't like that either when you're trying to figure out what in the world is she going to ask. That's not nice.
But is it going to be where we have the same kind of just silly story on the first quiz?
On the first quiz, I don't have anything on the review yet for that because I have not decided what to put for Chapter 1. So when I've decided what to put for Chapter 1, then I'll write it on the reviews that are posted in D2L, and we'll also talk about it in class on the day before the quiz. Okay. Does that answer your question? Kinda?
Sure.
Hopefully as we go along it'll get answered. Any other questions?
There's a late night cash one, so the one with,
The cash.
they all have the same amount of money in their pockets.
Is that this one?
Is that just that you take away 10 from, let's say, X, so then you have 10 less than...
I haven't read it lately. I'll read it again. Suppose that David Letterman and Paul Schaefer have the same amount of money in their pockets. How much must Dave give to Paul so that Paul would have $10 more than Dave? So if Dave gave Paul, who's giving the money? If Dave gave Paul $10, then Paul would have another $10, and Dave would have $10 less. So then there'd be a $20 difference. So like if Dave had $100, if they each had $100, and Dave, gave Paul $10, then Paul's at 110, but Dave's down to 90. So we don't want to do that. We'll just give $5. Because then Paul will go up to 105 and Dave will go down to 95, and that's a $10 difference. So yes, it does turn out to be half as much.
So it's always half.
On this problem, yeah. Yeah. So that's sometimes we try real life examples to try and answer questions that are not giving you a particular amount. We try a particular amount ourselves to see what works. Any other questions? Okay, let's go ahead and work on today's work. We've been looking at the pigeonhole principle in section 2.1. So the pigeonhole principle is a very powerful principle and yet very simple as well. Where did we write that out? Here it is. If we have more objects than we have boxes, at least one box must contain at least 2 objects. So it's kind of a simple idea, but it's very powerful. And the simplest example was with birthdays. If we had more than 366 people in a room, like we had 367 people, then there for sure would be 2 people with the same birthday, because there's only 366 days in the year if you count leap year. So if you have that extra person, there's going to be for sure 2 shared birthdays. Now there's might be more shared birthdays. Maybe nobody has a birthday on July 5th, things like that. So the pigeonhole principle gives us a big general answer that's definitive, but not necessarily the specifics. But it's very powerful for getting a general statement made. So some of the kinds of questions I'd ask you from this section are about the pigeonhole principle. So let's go ahead and try some of those questions out. I ask you to write them out because I think you remember things better then. So let's try an example. Must 2 people have the same SAT score of all the people who take the SAT on one of their regular exam days? And we're thinking in the U.S. here. Must 2 people have the same SAT score of all the people who take the SAT on one of the regular exam days? Let me see if I can straighten the document camera there. Okay. So go ahead and write down what you think. Yes, no, need more information. Yes, no, need more information. And tell me, what do you think? Yes, no, or need more information? And if you need more information, what do you need to know? Anybody? Yes?
Yes,
Yes. Okay. And why would you say yes?
because there's how many people that take the SAT scores, and it's not like there's a billion scores that you can get, so somebody would have to double up on scores.
So you're saying the most score you can get is low enough that more people are taking the SAT than that score that's possible. So the highest possible score is 1600, I believe. And more people take the SAT than that. So if we made little rooms for the people by their score, and we feel very sorry for the ones who were down here and scored, well, maybe they even scored 0, 1, 2, 3, 4, 5. And up here we put the people who scored 1,600 or 1,599. There's going to be more people than there are rooms. So at least one score will have 2 people in that room. Now we don't know which score, we don't know how many get the same score, maybe nobody gets some of the scores, but we do know for sure at least 2 people will have the same score. So that's why we say the word must. Let's try another question. How many 6-sided dice must be thrown? How many 6-sided dice must be thrown to be assured of a double? How many 6-sided dice must be thrown to be assured of a double? So when we say double, we mean 2 2s or 2 6s or 2 1s. So go ahead and write down what you think. Okay, so you have a cup and you can put as many dice as you want in it. How many must you put in that cup to be assured of a double when you dump them out? And we should say what's the least number, okay? So look for the least number of dice. Anybody want to tell what that would be? Did you write it down? What did you write?
The least amount is 2 dice to assure double. The most I believe could be 6.
So the least is 2.
Mhm.
So you could get a double with 2. But now we're going to want to be sure we get a double for sure.
Yeah.
So it couldn't be 2 then, because then we could have like a 1 and a 5. Okay. I saw your hand first. What did you say? 7. So why did you say 7?
Because theoretically you could throw a 1, a 2, 3, 4, a 5, and a 6. If you throw a 7th dice in there, it has to be another one of those numbers.
Yeah. So we're going to go for the 7, because that's the way we're thinking of it. We're like, we want to be sure that you have to get a 7. And you could get a 1 the first time, like you said, a 2, 3, 4, 5, 6. But once you've thrown 6 on the 7th throw, you have to be duplicating one of the other numbers. So you may have duplicated in 2, or you may duplicate in 3. You may get 2 of the same with 4. Anybody who plays Yahtzee knows you might get a pair with 5. But to be sure you're going to get a pair, you have to throw 7. We'll try some problems with decks of cards, because decks of cards are very convenient in a couple areas in this class that we'll look at. Now, in an earlier era, I would know you all knew how to play cards, because that's how people spent their free time. That's how I did anyway, growing up. But now I think most of you are on your phones. So let me describe a deck of cards. There's 4 suits: hearts, diamonds, clubs, spades. Hearts, diamonds, clubs, spades. And how many are in each suit? Anybody know? 13. Yeah, 13. So the ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So 52 cards altogether. So now I'm going to ask you questions about a deck of cards. How many cards must you draw to ensure 5 cards of one suit? How many cards must you draw to ensure 5 cards of one suit? So go ahead and write that down. Any poker players know what that's called? What do you call 5 cards of one suit? You call it big winnings. Oh, it's a flush. Okay. All right, so anybody want to tell what they wrote down? Well, let me give you a minute to think about it. So you want to ensure you get like 5 hearts or 5 kings or 5 diamonds. Now somebody said it. What did you say?
17.
Yep, 17 it is. And how did you figure it was 17?
I just did 4 times 4 and then added 1.
Good. So you could have 4 hearts, 4 diamonds, 4 clubs, 4 spades, without fulfilling the requirements. So it's not until you put that last 17th card down that for sure you're going to have 5 in one suit. So you could get 5 in one suit right away. Okay, you could just deal 5 hearts, but to be sure that you're going to get 5 of one suit, you'd need 17 cards, and then you'd be like, yep, there's 5 in here that are the same suit. So another question, how many cards must be dealt to ensure a pair? So go ahead and write down your answer to that. A pair would be 2 of a kind, meaning 2 queens, 2 threes, 2 sevens, something like that. I think we can do it less than that. Less than that. So you just have to have 2 with the same numbers. Anybody? Now you could do it in 2. What were you going to say?
14.
14 it is. Yep, 14. Good. 14, because you could deal 2 of a kind right away, but you didn't necessarily have to get 2 of a kind right away. If you went and dealt, you might get every single one different. Ace, king, ace 2, 3, 4, all the way up to king. But then on your 14th card, that would have to match one of the other ones. How about, we'll switch over to gloves. So I have a drawer with 3 pair of gloves. I don't really have a drawer with 3 pair of gloves. In my drawer there's like 8 right hands and no lefts. You know, that's how that goes. Okay, but pretend I do. I have a drawer with 3 pair of gloves. And the question is, how many do I have to pull out to be sure? How many do I have to pull out to be sure of getting a right and a left?
Four.
Boy, I didn't even get the question written, and you've got it figured out. 4. So that's exactly right. So you could have a pair in 2. You know, you could pick out a right and a left right away, but it might be that you pick out 3 rights first, and then when you pick the 4th one, for sure you'll get a left because there's no more rights left. There's no more rights available. So 4 is the answer. So those are types of pigeonhole questions that you could get asked on a quiz. Okay. And then there's a few more in your Mindscapes to practice with. So pigeonhole principle can tell us a definitive yes or no. We know definitively if we pull out 4 gloves, we're going to get a pair. We know if we have 14 cards of a regular deck, there's going to be a pair. We can tell definitively a big question like that. It's very powerful in that way. Do you have any questions on the pigeonhole principle? Yes.
I'm sorry, I'm just trying to like get used to thinking about stuff
Yeah.
like this, like these questions.
Yeah.
Can you go back to the how many cards must you draw to ensure 5 cards of one suit and explain that one? That's the only one
This
that.
one? Yeah.
Yeah.
So this one, you need to draw 17 cards to be sure to get 5 in one suit. Because as you're drawing cards, you could get a heart, or a diamond, or a club, or a spade each time. So you probably wouldn't need to draw 17, but you could have to. You could keep drawing and get 4 hearts. And then you draw some more and you get 4 diamonds. And then you draw some more and you get 4 clubs. And draw some more and get 4 spades. So that's 16 cards you've drawn, and you still only have 4 of each. But then when you get that next card, it's got to go in the room with one of the other suits. Okay. Any other questions? So as you do homework in 2.1, then on Friday we can go over that, because that will be due Friday night. So if you can make sure you know how to do it before Friday, then we can go over those questions. Did I say Friday night? Your homework will be due Sunday night, but I'm not meeting with you Saturday or Sunday. So try and go over that today. We're going to turn our attention then to our next section. So the author starts out these sections with a question, and this question is missing. No, where did it go? Here it is. What is the next in the sequence? Pine cone, pineapple, daisy, and so on. So we're going to look at your pine cones and pineapples. Hopefully everybody brought a pine cone or a pineapple. I see some of them, so that's super and delicious too, at least if you brought the pineapple. So we're looking at what is the next in this sequence? Pine cone, pineapple, daisy. What comes after that? So I'll just put some stuff down here, okay. So you should take out your pine cone or pineapple and examine it and start making observations. Think about what pine cones and pineapples and daisies have in common. I have a few extra that the first class left for you. I think they just didn't want to throw them out. But if you didn't bring a pine cone, you can take one of these then. Let's send it down in this section, and then in the back, pass it across and end up here. So please pass that down if you don't have a pineapple or a pine cone. So just be observing that, and talk to the person around you if you want to, and see if you can figure out what kinds of observations might we observe that are in both bunches.
Can there be like patterns? Have that pattern of things that stick out in rows, and then Daisy has the pattern of the
Yes, I can see it. I am thinking probably
No, we're not having
Towards the top.
This one for physical makes more sense if we have an empty list.
Okay, so what kinds of questions do you, what kinds of observations do you have? Yes,
I'm noticing the spirals,
the spiral.
all of them,
You know what they do? They all have spirals.
including the daisies and flowers.
We're actually going to count the spirals. So we're moving from qualitative to quantitative. So we're going to count spirals today. So with your pine cone, I have marked off some spirals. See if that shows up. Okay, so I marked these off with silver and brown, so you can see the alternating spirals. So here, one coming here, one coming there. So we're counting how many spirals they have, and I'd like you to count how many spirals your pine cone or pineapple has. Now don't count the individual nodes, okay? And if you have a marker, it helps. So this one, somebody took a marker and drew, so they could see every other one. That is, in fact, most helpful. So we're counting not the nodes in the spiral, but the spirals themselves. How many spirals? So, for example, on your pineapple, take your pineapple. Here you have spirals here. Here's one row that my thumbs are on. Now my thumbs are on a second row. Now my thumbs are on a third row. And it's kind of tricky because your row comes up around, so you have to really be careful.
Wait, so these go like up and down.
Count the spirals, and I'm going to come around and ask you how many spirals you found. Yes? Question.
How are we counting the spirals in the center?
So one spiral is one diagonal. So this one that my thumbs are on goes all the way down behind here and all the way up here, and that's one. And then I go to here, and that would be two. With a pine cone, you're easier to start at the bottom. Yes. Absolutely. Pick a good one.
Another thing is she just wants us to repeat.
I had a tiny one like yours and then it kind of broke and spotted.
Oh, here, I'll give you the
And I
basket.
forgot to print out the 2.2.
Okay, how many are you finding? Anybody? Once you found in one direction, go the other direction. So you have spirals going in both directions. You should be able to get the same amount as the people next to you. So you have spirals going one direction, so here these are going up to the right. But you have spirals going down to the right as well. Okay?
Around 9 or 10.
This is something Fibonacci did in the 1300s, I believe. This is what you can do when you don't have internet.
9.
How many did you get?
9.
Anybody, what did you get with your pineapples? 10. You both got 10? Which direction? Going the other direction, what did you get? All three, what did you get? You got 9? You could have a malformed pineapple, but it shouldn't be 9 or 10. It should not be 9 or 10 on your pineapple. What did you get? 9. Is that 9? We can't all have malformed pineapples. Okay.
Be careful,
It's leaky.
We got it last Friday.
Oh, you were on the ball. It's going to be very sweet when you open it. Okay, so put your thumbs carefully on one row. Go the easy way first, and hold your thumbs there, and let your person next to you help you count. Okay? Or keep your hand there carefully. How about pine cones? What are you getting for your pine cones?
10, 11, Well,
The other way around.
this is the fun part. It's too early in the morning. It's noon. Darn it. Trying to think.
They don't spiral around.
Ball spirals. What should-
Yeah.
I think if you like,
Because they all spiral to the middle.
so they, yeah, just.
What other numbers are you getting? 6? Should be 6. 8 it is. 8 is one way. What did you get?
Never mind.
What did you
When I
get?
counted the other way, I got 14.
13. Oh, yeah. So you're off just one. So the one that's our 9 are off just one as well. Okay, I'll write down what you should get if you have a pine cone. No chipmunks have been eating. And a pineapple. Nature is messy. Okay, so a pine cone will have 5 spirals going one way and 8 another. So I'm going to take these ones that are formed pretty nicely that I use paint on to show you. Okay, so you see 4 silver spirals. 1, 2. Let's see. Oh wait, is this? Let me look at a better one. I have several of these. This one's better. This one's better. Okay, so we have 4 silver. 1, 2, 3, 4, going counterclockwise, and 1, 2, 3, 4 brown going counterclockwise. And then going clockwise, where's one that's pretty good going clockwise? It's probably the one I heard rolling away under my desk as I left. Okay, so these are going counterclockwise, so there should be 8 there, so that's not one. This one is going clockwise, so this one should have 5. Let's check. So we have 1, 2, 3 silver. These 2 are right next to each other. And 1, 2 brown. So 5 going clockwise, 8 going counterclockwise. The counterclockwise are easiest to see because you can alternate the colors. And if you have a pretty decent pine cone, you can pick that out. The pineapple, I did count this, and it does have 9 and 13. I'm sorry, 8 and 13. So I actually stood in the grocery store counting the stripes until I made sure I had a good one. Might look kind of weird. All right. So then we have daisies. Daisies will be easier to count because I brought you a photo. Online students, you can print this photo off. It's on D12 content. So we have the daisies. Not only is there a photo, but the spirals are drawn in to help you so you can see a little better. So go ahead and count these, please. So when you have the right number of spirals counted, confer with the person next to you, please, and we'll see if we can all come up with the same thing. And by the way, you do need to take a picture of you with your pine cone or your pineapple for your Dropbox activity today, okay?
So for the pictures, we have take a picture of her face and the pineapple?
You don't have to be in them if you don't want to, just so it's
Okay.
clear it's a real pineapple. Sometimes I have people Photoshop and you're like, you couldn't, go outside, go to the grocery store. I love seeing people's faces with the pineapples though. I think those are great photo ops. Yeah, those are your pictures to keep, so feel free to draw on them. That'll make it easier. How many did you find? 21 and 34. Yep. 21 and 34. So the question in this series is, what is the next term in the sequence? We had pine cone, pineapple, daisy. What next? What next do you think would possibly have those spirals, and we're getting more and more of them?
Roses.
Pardon?
Roses.
What's it?
Roses.
Roses. That's a very good question. I wonder if roses have that number of petals. And did you say pine tree?
Yeah.
I wonder if the branches grow out like that.
Yeah.
That would be interesting to find out. Would be
The
very
one at my
interesting.
house has it.
Very interesting. Well, the one that I was thinking of, and the author is thinking of here, is sunflower.
Oh, yeah.
So a sunflower has 55 spirals going one way and 89 the other. So let's lay these numbers out in order. 5, 8, 21, 34, 55, 89. You could put some other things I know that would fit in here would be bananas. They have 3 cross segments. Apples, I believe, have 5. So, does anyone see a pattern here? What would the next number after 89 be? Not as a vegetation, but as an actual number. What would the next number be?
94. Am I close?
Not 94. 144.
Oh, okay.
Yep. Yep. And how did you get 144? Good. So this is called the Fibonacci sequence, and this Fibonacci sequence does have each number formed by adding the 2 before it. Are you working on the Mindscape?
I was just helping her out.
Okay. Make sure you bring Mindscape questions to class then on next class, because we'll have questions to go over. So you can add 5 and 8 and get 13. 8 and 13 add to 21. 13 and 21 add to 34. 21 and 34 add to 55, and so on. So we could just keep going. Let's put the next couple numbers down here. 89 and 144. 233. 233 and 144. 377. So we can keep going on with this. How far could we keep going on with this?
Infinitely.
Yeah, infinitely. How about the other direction? How would we find the number that would come before the 5?
You'd subtract them, wouldn't you?
Yeah. So what number comes before the 5?
3.
Yep, 3. Good. And then what?
2.
2. Now
1.
1. And now what? 1. We're going to stop there, but the Fibonacci numbers can be carried back through 0 and the negative numbers as well. But we're going to stop here and title these the Fibonacci numbers. the Fibonacci numbers are derived from nature, from looking around, and they make this interesting sequence that you add the two numbers before and you get the next number, and those numbers show up as a regular part of nature. The ratios actually also turn out to be of interest. So when we say ratio, we mean to make a fraction. So we'll make a fraction of successive Fibonacci numbers. Now you can do the ratio forward or backwards. I'm going to do the second number divided by the first number. So 1 divided by 1, 2 divided by 1, 3 divided by 2. Next would come 5 divided by 3, and then 8 divided by 5, 13 divided by 8, 21 divided by 13, 34 divided by 21, 55 divided by 34, 89 divided by 55, 144 over 89, 233 over 144. So I'm just writing these down as fractions. We're going to get their decimal approximations, and we could keep going further and further if we like, but I think we'll stop here. So 1 divided by 1, that's just 1. 2 divided by 1 is 2. 3 divided by 2 is 1.5. I'd like you to do these other ratios. You'll need your calculator probably. And I'd like you to go ahead and do this to 4 decimal places. You can round on the 4th decimal place. Remember when you're rounding, if the decimal place after is 5 or higher, then you round up. So if you had something like 1.23741, you would just truncate. But if your 5th digit is 5 or higher, then you round up. So go ahead and do that. Now I don't want everybody has to do all this. So how about the front row does the first column, the second row does the third, the second. Okay, here. Okay, front row here. Second row here, and third row here. And then I'll try and pick people I haven't heard from or don't remember hearing from today to tell me what these numbers are, okay? So you just have to do your column, and then we'll do the rest. We'll fill this in together. Okay, so we're going to start up in the front here. What did you get for the first one? What was 5/3?
1.66 repeating.
Okay, 1.66 repeating, so that means we round that one to 7. Great. Okay, and then what was yours? 8/5? What was it?
1.6.
1.6. So that one just ends, so we'll just put zeros there. And then I think I heard from you, I don't remember hearing from you way on the end. What was 13 divided by 8? So that one just ends too. So we'll go ahead and put 1.6250. Okay, second row. Can you tell me the first one, please?
1.6154.
And the next digit after that?
Oh, I rounded that already. It was an 8. It was a 61538. So I just rounded that to 4.
Okay, so we're going to keep 4 decimal places. So 1.6538. Thank you. Okay, I remember hearing from you. I don't know if I heard from you. Can you tell me what you have, please?
1.6190.
190? Did I hear that right?
Yes.
Okay, thank you. And then, did I hear from you? What is yours? Next one.
1.617.
1.6176?
Yeah.
Okay, great, thank you. Okay, you answered. What did you get for this one? 89 over 55.
1.6182.
Okay, great. 144 over 89, what did you have?
I had 1.6180.
Okay, good. And one more, 233 over 144, what did you get for that?
1.6180.
Oh, the same? I think these might have been a little different.
Let me see. Maybe I wrote it down around the phone.
Yeah, somebody might have, I don't know.
Yeah, I got 1.610.
Okay. I'm going to check.
The number after 0 was 5. I made round it up to a
So
1.
it would be like 1.
Okay, right here?
Yeah.
Okay.
Round up to a 1.
All right, thank you. And we see this number then, we could say that it's approaching a value. We could make these ratios go on and on, just like the Fibonacci's go on, and we'd see that we're approaching a particular value. And from just these ratios, we can see that we're constant now in the third decimal place, right? So we can say this ratio approaches 1.618, and then if we wanted to know more decimal places, we could do more ratios until we can see that the fourth decimal place is staying the same, and then we could go further to see that the fifth decimal place is staying the same. But I think this is far enough. So this ratio we did with the larger number divided by the smaller number. Sometimes it's done the other way around. In fact, when it's used the other way around, it's part of an investment scheme. So the Fibonacci numbers play a role in the Elliott wave investment scheme. If you're a market analyst, that would be something that would be in your toolbox of ways to work with the stock market, surprisingly enough. We'll go from vegetation to the stock market. We're going to look at these ratios in a way that lets us write them all with ones. We're going to be able to rewrite all these ratios with just the number 1, which I think is amazing that you can do that. So we have the ratio 1 over 1. That's clear. That's just written with 1. Then we have the ratio 2 over 1. So I'm going to think of the 2 as 1 plus 1 over 1. And I'm developing a pattern that I'm going to be using in the future ratios. So now I'm going to split this up. I'm going to think of it as 1 over 1 plus 1 over 1. And the first 1 over 1 I'll just call 1. So that was a really weird way to write 2 as 1 plus 1. But I'm getting a pattern going, because now I have 3 over 2. And the 3 I'm going to break up like I did the previous ratio. So I'm going to write the 3 as 2 plus 1. So the 3 is 2 plus 1, and then I can make a fraction 2 over 2 plus 1 over 2. So when you have fractions like this, if you want, you can split it up. Just like when you're adding fractions, if they have the same denominator, you add them up. So I have the 2 over 2 is a 1. And to make my life easier, I'm going to use the work I did ahead of time to rewrite the 2. So here's 2. Well, I already wrote 2. I wrote it like this. So now I have a really complicated fraction, a fraction with a fraction in it. These are called continued fractions, and you can have a whole class on continued fractions. In graduate school, I took a semester on continued fractions. Okay, so we have 3 over 2, and now we're looking at 5 over 3. So the 5 is a 3 plus 2. We're following the pattern that we did before. So we break up the 5 as 3 plus 2, because that's how we get it in the Fibonacci numbers, right? It's 3 plus 2. And then we split this up. So the 3 over 3 is a 1. Can you save your conversation for later, please? The 3 over 3 is a 1. The 1 over 2 over 3 we're going to do math. I wrote that down wrong, didn't I? The 2 over 3 I'm going to write as 1 over 3 over 2. So when you were in algebra class and you had a fraction in the denominator, does anyone remember what you did with it? Good. Yeah, you flipped it and multiplied it. So we did that backwards. So when you had a fraction in algebra class in the denominator, you'd flip it and change to multiplying. And so that's all that we did there, except we did it backwards. The reason we did that is so that we can use the work above. So the work above was to figure out 3 over 2, and we did that. It's right here. So we can go ahead and fill that in. So I'm going to fill in the red 3 over 2. And we can keep doing this. We can keep using the work that we did above to get the continued fraction describing the ratio all in ones. So how about we do that one more time. 8 over 5. We split the 8 up. 5 plus 3 over 5. Okay, then we split up the 5 plus 3 over 5 into 2 fractions. And then I'll go a line below because I wrote that too close to the other. So the 5 over 5 is 1. And the 3 over 5, that's not going to fit with my pattern, so I'm going to rewrite it as a 1 over 5/3. And then that's a big help because I already figured out how to write 5/3 with just ones. So here's my 5/3 with just ones. Just have to make sure you don't miss any. So what do you think the 100th ratio would look like? We did the first ratio, second ratio, third ratio, fourth ratio, fifth ratio. What do you think the 100th ratio would look like? Well, you can think about that, and we will talk about it on Friday. What does the 100th ratio look like? Okay, I'll see you on Friday.